All right, party people, let's do it to it. Okay. Researchers investigated how the size of a bowl affects how much ice cream people tend to scoop when serving themselves. This is the idea of priming, right? If you give them a bigger bowl, are they just going to think about putting more ice cream in it? At an ice cream social, people were randomly given either a 17-ounce or a 34-ounce bowl, both large enough that they would not be filled to capacity. That's what they think. They were then invited to scoop as much ice cream as they liked into their bowl. Did the bowl size change the selected portion size? Justify your answer at a significance level of 0.05. Okay. If giving a significance level isn't a hint that you should do a hypothesis test, I do not know what is. Definitely we should be doing a test, even if it just says justify your answer. So it's a hypothesis test. I'll start with our hypotheses. Hypotheses. And I'm going to say that mu1 is the mean for people with a 17-ounce bowl. And mu2 is the mean for people with the 34-ounce bowl. So then, since it's two means, and I'm comparing them, my null is always going to be that they're equal to each other. Mu1 is equal to mu2. Mu2. The alternative hypothesis is, well, the smaller bowl had a smaller mean. So our alternative hypothesis is going to be that mu1, the 17-ounce bowl, actually results in a lower mean. There's an argument here for a not equal to. We could double our p-value and see, but when we get there. All right. Hypotheses. Now, a couple of things to notice in terms of grading FRQs. We defined them, but we also have to define, if we're using multiple means or multiple proportions, you have to define what mu1 and what mu2 are. This will also help you because it will help you not get your hypotheses backwards and end up with like a 0.99 p-value. All right, cool. Hypotheses. Next, we've got preconditions. They are pre because they must be met. These need to be met for both means. So first up, for independence, we've got randomly selected. Or I'm actually going to say that this is randomly applied treatment. Right? They were randomly given either a small bowl or a big bowl. Then our other check for independence is that it's small enough that our sample size is less than 10% of the population. Kind of any number of people you could interact with is less than 10% of the population, but we can definitely say that the 36 and the 32 people, don't abbreviate, people are both less than 10% of all people who eat ice cream. And last, we're going to check for normal. So first, if the distribution of a population is normal, it's normal. It doesn't say anything about the population distribution, so can't go with that. Next, if the sample size is greater than 30 for both groups. So small bowl, n was equal to 36. 36 is greater than 30. So we are checked off for normal on our small bowl group. Then our large bowl, n was equal to 32. 32 is also greater than 30. Greater than or equal to 30. So we're checked off there as well. Okay. Now, shocking nobody, I ran out of room. We're going to shrink this stuff down because we've done it. Hypotheses and preconditions. Y'all are doing pretty well with those. After that comes our formula and then our calculations. So the formula, this is where you want to say the test you're doing. So what we're doing is a 2-sample t-test for means. And our t-value we're basically looking for the probability that the t-value we get is less than a specific value. So we'll get that actually from our calculations. So it's just going to be like our value minus our other value over the standard error. So let's look at our calculations. So we're going to do a 2-sample t-test in our calculator. So we go to stat calc, or excuse me, stat tests, 2-sample t-test. Okay. We're inputting stats because we have the statistics. We don't have the actual data points. So for X1, since we defined mu1 as the mean for people with the 17-ounce bowl, all of our ones are about this. So X1 is going to be 5.07. The standard deviation or standard error from 1 is 1.84. And then N1, our sample size, is 36. Next up, we have the big bowl, X2, SX2, and N2. And those are all going to be 6.58, 2.91, and 32. Last but not least, our mu1 should match our alternative. So we think mu1 is less than mu2. All right, give me a second to put all this in my calculator. N1 is 36. And we think mu1 is less than mu2. We're not going to do this pool. It's never wrong to not pool for AP stats. And we get a t-value of negative 2.52 and a p-value of 0.0074. Now, I'm going to take this t-value, put it right here. So our t-distribution, the reason I didn't do this completely by hand is it takes into account our degrees of freedom and it just gets a little more complicated. So I'm just going to let the calculator do it because you always have that available. And then we're just showing that it's less than that. So the probability that there is no difference, that this is true, and we got results like this, is about 0.7%. And so this is why we don't really even need to worry about a two-tailed test, because we would still come to the same conclusion even if we doubled that p-value. So after calculations, we have our conclusion. Always the same conclusion. Slightly different context, always the same words. Because our p-value of, use this actual number, BS, 0.0074 is less than our significance level of alpha is equal to 0.05, we reject the null hypothesis. And you can use HO here too. Okay, that is sentence one. The first sentence is about the null hypothesis. Sentence two. You can even bullet point that. We have convincing evidence that the mean ice cream serving size in the 17-ounce bowl is less than the mean serving size in the 34-ounce bowl. So this one is about your alternative. This one is about your null. Right? So you talk about the null first. Are you going to reject or fail to reject? In this case, we rejected because it was lower. P is low, reject the Ho. We have convincing evidence. Our second sentence is we have or we do not have, depending on what we said here, evidence that whatever the alternative hypothesis was. So always one about the Ho, one about the Ha. Great. We answered this question. Did the bowl size change the selected portion size? Probably. Then create and interpret a 95% confidence interval for the difference in mean ice cream serving size from the problem above. How does this compare to your conclusion? Okay. We should expect, since we found a significant result at a significance level of 0.05, we should expect a 95% confidence interval for the difference to be all negative or all positive. It should not contain 0. As long as it doesn't contain 0, it matches. It's evidence of there being a difference. So here we start with preconditions. They are the same as above. We're going to say checked above. Then our formula, this is now going to be a 2 sample Z interval, or excuse me, 2 sample T interval. This is a 2 sample T interval for the mean difference. And maybe I should have called this for a mean difference. And it's basically going to be, this should, we'll keep it all negative. So we'll say mu1 minus mu2. And those are defined above, plus or minus the critical value. This is going to be T star. Again, we're going to let the calculator do this because it's complicated by hand. Not that bad. And then it's going to be the standard error of mu1 minus mu2, which is basically just the square root of the standard deviation squared over the square root of the sample size. It's on your formula sheet. That's great. So the interval. It should already be in your calculator from doing the hypothesis test. So all of these are exactly the same. They're all still in there. The only thing you need to change is you're going to make sure your confidence level is at 95%. When we calculate this interval, we get negative 2.712 to negative 0.3078. Why did that go to more decimal places? That's interesting. So for the conclusion here, We are 95% confident that the interval, and we can kind of go either way here. Negative 2.712 to negative 0.3078 contains the difference mu1 minus mu2 in serving sizes between the small bowl and big bowl. You might say the actual ounces. I'm running out of space. Okay. So because this interval does not contain 0, we would expect a significant result at the 5% significance level, right? 5% goes with 95%. If we got an interval at 99% that didn't contain 0, we'd have significance at the 0.01, at the 1%, right? They sort of complement each other. Let's keep going. Okay. Another hypothesis test. In 1998, as an advertising campaign, the Nabisco company announced a 1,000 chips challenge, claiming that every 18-ounce bag of their Chips Ahoy cookies contained at least 1,000 chocolate chips. Dedicated statistics students at the Air Force Academy, true story. Apparently they don't have enough to do. That doesn't seem right. Purchased some randomly selected bags of cookies and counted the chocolate chips. Some of their data are given below. So this is, I believe, 16 data points. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay. What is the sample mean, X bar, of this sample of the student's data? I'm going to pop this in my list. So I'm going to go to edit list, and I'm going to put this in carefully. I have been known to make mistakes typing stuff into my calculator. Oh, 58, 1356, 1132, 1191, 1270, 1295. All right. And 1135. Okay, so 16 data points. I'm going to go to stat, calc, 1var stats. I do not have a frequency list. Make sure to clear that out if you have something in there. And the sample mean, so X bar, is equal to 1,238.1875 chocolate chips. Ounce bag. Okay, done. Given your answer to part A, set up, perform, and conclude a hypothesis test. Why did I do this to myself? Okay. Let's set it at the alpha equals 0.05. Didn't say, so let's default to that. So our hypotheses, well, this is going to be a one sample t-test, and our hypothesis, I would say, would be that the actual mean is greater, right? They're saying it's at least 1,000. I'm going to say that it's greater than 1,000. So, the null is going to be, this is a colon, this is going to be that mu is equal to 1,000. And the alternative is that mu is actually greater than 1,000. Right, because our mean was a lot bigger. Next, we've got our preconditions. Okay, random. It says randomly selected bags of cookies. So problem states randomly selected bags of cookies. Small enough. So these are both about independence. 16 bags is certainly less than 10% of all bags of cookies Nabisco makes. And Chips Ahoy cookies, be as specific as possible. Normal. Well, we don't know anything about the parent population. We definitely don't have a sample size greater than 30. So now we're going to have to go to our stat plot. And I'm going to make a histogram of my list. So you go to second y equals and turn your stat plot on, select the picture that looks like a histogram, and then make sure your X list is L1. And then I would hit zoom 9 for zoom stat. That's going to zoom you pretty nicely. And so I'm going to sketch my histogram. So we've got like this, and like this. So it's a little bit skewed, right? But I could change my window and probably get a more normal distribution. So the X scale I'm going to make be 50. Yeah, that gives me a much more normal. So you can mess around a little bit with your scaling. So I have like this, and then like this, and like this, and this. So I'm going to say data is free from strong skewness and outliers. So that's normal enough. After preconditions, we have our formula. And this is where we name our test. So this is going to be a one sample t-test for a mean. And we're looking at the probability that t is greater than whatever t-score we get. So when we calculate it, just turn my plots off real quick. And we're going to go to stat tests. And this one is just going to be called t-test. And we have the data this time. So from the data, we're going to say the mu naught we think is 1,000, right? That was from our null hypothesis. The list, we're going to have L1. That's where I put my data. Frequency, just leave it as 1. And our alternative is that our actual mean is greater than the null. So this should always match your alternative. Okay. So when we calculate that, we got a really, really gigantic t-score. Okay, so the t is 47.355, and the p-value. Now be careful with a p-value like this. It's 4.74 times 10 to the negative 18th. If this number is bigger than 1, you will lose that FRQ. If this number comes out bigger than 1, there is going to be some scientific notation. Find it, write it down. It is completely wrong and shows like a fundamental misunderstanding of probability if you give them a value greater than 1. Don't do it. All right, good. Now, our conclusion. Oh, man, making you guys do a lot of work, huh? I need to give myself some more space. Shrink down my hypothesis test here. Like, all right, so conclusion. Okay. Because this first sentence is about the hoe, because our p-value of 4.74 times 10 to the negative 18th, so that would be 17 zeros to the right of the decimal point before we get to the 4, is far less our alpha of 0.05. We reject. If the p is low, reject the hoe. The null hypothesis. That's our first sentence about the null. We have convincing evidence that the mean number of chips per bag is greater than 1,000. All right. Chips Ahoy and Nabisco, they are not playing around. They are definitely meeting that 1,000 mark because they know someone out there is going to count it. All right. Good. Hypothesis test. Given your conclusion in part B, what type of error might you have made and explain what this means in context? Okay. Here's our error box. This is when the null is true. This is when the null is not true. This is P is below alpha, so we reject. This is P is greater than alpha, so we fail to reject. Remember, accept nothing. I'm going to say that over and over and over again. If the P is low and the null hypothesis is false, this is not an error. That's a correct conclusion and outcome. If the null is true and we failed to reject the null, also correct, not an error. Type 1 is when the null is true, but we reject it because we just got one of those weird edge cases. We were really to the left or really to the right on the distribution of possible sampling on the sampling distribution, but we're still in the mix. Type 2 is when the null hypothesis is false, but we failed to reject it, right? We were just too close to the null. Okay, cool. So because we rejected, right? We rejected. The only type of error we could make is a type 1 error. So we could have made a type 1 error. This would mean that the number of chocolate chips per 18-ounce bag is actually 1,000, but we say it's more. The consequence, this is a pretty light consequence, is less chocolate than we think. We're getting less chocolate than we think, fewer chocolate chips. Not a super terrible consequence in the scheme of things. Create and interpret a 90% confidence interval for the average number of chips in bags of Chips Ahoy cookies. Okay, so this is for one sample. And excuse me. So this is going to be a T interval, just a T interval for the number. And we've checked the conditions already with our hypothesis test. The formula. So if you didn't do a hypothesis test, you need to check the conditions if you're making an interval. I'm just not rechecking them because they're literally those. All of those. Okay. formula is going to be mu plus or minus t star times the standard error. Oops. Of x bar. Oh, sorry, that's not going to be mu. That's going to be x bar. I made an error earlier. Up here on this interval. These shouldn't be mu's. These should be, when we do confidence intervals, those are x bars. So are these. Confidence intervals, we have x bars. Hypothesis tests, we have mu's. My apologies. I don't know if I'm tech savvy enough to go and change that in the moment. It will be correct on the answer key now. All right, cool. There's a formula. And the interval we're going to get from our calculator. Stat tests t interval from our data. And we want a 90% confidence level, so make sure you change that. So our interval is 1196.9 to 1279.5. So our conclusion is we are 90% confident that the interval 1197 to 1280 chocolate chips contains the number of chocolate chips per 18-ounce bag of chips. Ahoy. Okay, sweet. I'm going to take a little break. Part 2 coming to you so soon.